Alright, welcome back everyone, and we are now finally ready to do the H1 NMR, or also known as the Proton NMR section of the course. So this is the last lecture portion of this course. There will be a practice session to wrap things up in one final session, but this is going to be the last of the lecturing material. And just as a quick reminder, you can always go over to chemcomplete.com. If you want further training, we offer one-on-one sessions, and you can also buy the spectroscopy guide that I wrote, which comes with additional practice questions and has a more detailed outline of everything offered in this free course. So let's go ahead and get started. When we deal with Proton NMR, there's a couple things to keep in mind that's different because we're just coming off of carbon-13 NMR. The most important is that we're dealing with coupling almost all the time now. So coupling is when we talk about peak splitting. So this is, for instance, when you talk about having a doublet or a triplet or a quartet. When you have that type of fracturing of your peaks, that's known as coupling. And this utilizes the N+1 rule. So I'm not going to go into this in great detail. I have additional videos on the channel that relate to how splitting works and how coupling works. And if you are interested in knowing why the N+1 rule exists and how it is utilized, you can take a look at those videos. However, the general summary of the N+1 rule is that N is going to equal the number of neighboring protons, and then you add 1, and that will be what the signal splits into. So for instance, if I have a CH3 neighboring a CH2, then this CH3 has 2 neighboring protons found in the CH2. So therefore, it will turn into a triplet. And again, that's because N would equal 2 in this case, the neighboring protons, plus 1 is 3, so that's a triplet. And then if you take a look at the CH2 has a neighboring methyl group, and that's 3 neighboring protons, plus 1 would be 4, so that would be a quartet when we look at the splitting patterns. Alright, so that's a general summary of the N+1 rule, but it's going to be important, and we will be applying it all the time when we're trying to utilize HNMR. Now, this is the most valuable technique in terms of structural information, because as you can see that we just did right above here, the methyl group and the CH2 group, they give information about what they're next to based on their coupling and their splitting patterns there. So when you get to HNMR, it's probably the most valuable of all of the spectra because you are able to, provided you have coupling on, you are able to determine a lot about the arrangement of the protons. So it starts giving you a lot of information regarding the hydrocarbon skeleton of whatever compound you're looking at. So let's take a look at a general summary. This table is a little bit shorter than the carbon table. All right, so type of protons that we can have. You can have an alkane hydrocarbon, which is sp3 hybridized. So these are your CH3, CH2, CHs, and that's going to have a general range of 0.7 to 1.5. So the CH3s, the methyls, are going to be the lowest on the ppm scale. They would be the most shielded, and then as you continue to creep up all the way to the methane, which is going to be the CH, that would be a 1.5. Then you have any type of hydrocarbon that might be an alkyne or a resonance hydrocarbon, and that's going to be 2.0 to 3.0 on the relative scale. So when you're talking about something like that, you are talking about hydrogens that perhaps are involved on an aromatic ring. If you're talking about a hydrocarbon like a methyl group on the aromatic ring. So not to mistake that with aromatic hydrogens that are actually on the aromatic ring itself. Then you have hydrocarbons that are near electronegative atoms. That's going to be 3.0 to 5.5. So these are going to be, for instance, your methyl groups that are next to oxygens or your methylenes that are attached to a halogen or something like that. Then you start to get further up when you get into alkene hydrocarbons. So these are going to be the hydrogens directly attached to carbon-carbon double bonds. Those are going to start going north of 5 ppm to about 5.5 to 6.5. And then right after that, similar in nature are the aromatic hydrogens. Those are going to be a little bit further up. 6.5 to 8.5 would be the relative range for those. And when we talk about aromatic hydrogens there, those are hydrogens directly attached to the aromatic ring. Then the last two are usually very unique. They're easy to identify as singlets, and that is the hydrogen associated with an aldehyde. So when you have the C double bond O and then the aldehyde has an H over here, this proton right here will show up as a singlet because there's no neighboring protons, and it will appear between 9 to 10 ppm. And then you will also see the same sort of behavior for a carboxylic acid hydrogen. So for a carboxylic acid, we're simply putting the extra O here. And then this hydrogen would also show up as a singlet, and it would be around 11 to 12 ppm. So these are rough guidelines. You don't want to take them as complete gospel when you're dealing with organic chemical shift. However, you should know that if you see, for instance, a peak down at 1.2 ppm, it should not be associated as an aldehyde hydrogen. That would not be appropriate. All right, so a couple of general rules here. If you missed the last lecture on carbon-13, I would strongly encourage you to go back and look it over because I'm referencing it here. But as with C13, we're going to check for the general chemical shifts that will be useful. So in the previous lecture, we went over a whole checklist of here's what we should sort of look at and glance at when we're first approaching an NMR. And this is the same for the hydrogen NMR, and then you would add, looking at the splitting and the integration on top of that. So with the carbon-13, we would check for the general chemical shifts to see what was useful. So we'd look at our ppm scale and we'd say, oh, I see I've got some in the aromatic region. Oh, I see I have a carbonyl, something like that. So you want to do the same thing here. If you're glancing at one of your NMR specs and you see that you've got some peaks showing up between 6.5 and 8.5, you would know just by looking at that, before you even get into splitting or integration, oh, I have some aromatic activity here, so I should probably check and make sure that that's something plausible with my degrees of unsaturation, my IR, things like that we've discussed. So you're going to use, as I just mentioned, the information from all previous spectra to support the claims that are made here. So this is where you're wrapping things up and you're putting the final structure together, but it should always be backed by other examples that you have from the other spectra that we've come across. That can include mass spec, IR, carbon-13, and also your degrees of unsaturation should not be violated. So if you only came up with, for instance, 2 degrees of unsaturation, it would not be acceptable to start proposing an aromatic ring at that point. If you're proposing a carbonyl, you should also be able to find the carbonyl in the carbon-13, and you should see the vibration in the IR spec. So these are examples where you're supporting your evidence further based on what you already looked at. All right. Now, an example, you find aromatic peaks at 7 to 8 ppm. You should be able to find an aromatic signal in your C13 and aromatic vibrations on your IR. Your degrees of unsaturation must also support this. So that goes along the lines of what we were just talking about. Then you also want to confirm your integration numbers and make sure that they make sense. Then you spend the rest of the time analyzing the splitting pattern. So once you have your general outline, your chemical shifts, you've got a rough idea of what you might be dealing with, then you go through and you look at your integration numbers. Do the integration numbers make sense? Okay, so especially if you have your chemical formula, right? If you were able to calculate degrees of unsaturation or you have found it out through mass spec or something like that, you know how many hydrogens and carbons there should be. So when you're looking at your hydrogen NMR and your carbon NMR, you should be able to take a tally of that and see if it matches. So for the hydrogen NMR, all of the total peaks should add up in terms of their integration to the total number of hydrogens in the structure. So then you finally analyze the splitting patterns, and that is looking at what is next to what. So let's take a look at some examples, okay, before wrapping this up, and then we will go on to the practice session next. And that is where we will tie all of this together. We'll do an example that has everything starting with degrees of unsaturation all the way down to the proton NMR. So I'm going to keep these structures relatively simple because we're doing it only in the context of the proton NMR. We don't have any supporting carbon or IR or anything like that here. All right, so let's take a look at this. We've got C4H8O2, and if we take a look at the structure here, I see an integration of 3, 3, 2, and I see a triplet, a singlet, and a quartet. Right? Now, in terms of the approximate location, this might be a little small, so I'm going to write it out here. The chemical shift for this peak is about 1.2 for the triplet. All right, it's about 2.1 for the singlet, and then for the quartet, you're looking at about 4.2. So we know that one must be the most de-shielded. Right? Now, before we even do anything else, and we could calculate degrees of unsaturation, we want to take a look at this real quick. We don't have any type of aromatics or carbon-carbon double bonds. However, we do have some electronegative behavior here with some de-shielding. So what would probably make sense if we see something that's all the way up at a 4 to a 4.5, and we do with a 4.2, then we're probably dealing with something directly attached to an oxygen. And that's just because if you go back and you look at our table up here, right, when we get to the 3 to 5.5 range, it's hydrocarbons that are directly associated with or near electronegative atoms. And so if I were to take a look at this, I probably have some sort of a CH2 group based on the integration next to an oxygen, right? And then what I can also determine from that point is that I likely have, because this is a quartet, a CH3 as a neighbor because of the N+1 rule. So I would have a CH3 as a neighbor, right? Now that would be terminal because the CH3 cannot have anything else bound to it. So that's one end of the molecule right there. Now what I also want to confirm is if I did this correctly, then I should find the CH3 signal as a triplet and it should integrate to 3. And sure enough, down at 1.2, I see a triplet that integrates to 3. So this is most likely going to be one section of my compound. Now the question is, what do I have left? Well, you can start taking away from the equation that you have up here. So if I have 2 carbons that I've already used, that's going to make it C2. If I've used 5 hydrogens, that's going to make it H3. And then if I have used 1 oxygen, that's going to make it O. So that's what I have left. 2 carbons, 3 hydrogens, and an oxygen. All right. Now, if I look at 2.1, that's getting pretty far up. So I probably have some sort of a resonance, meaning either an aromatic or carbonyl type of behavior. And I definitely don't have aromatic. So for right now, I'm just going to propose that I have a carbonyl and see if the rest makes sense. So if I get rid of 1 carbon and the last oxygen, that leaves CH3. So would this make sense? Could I have a methyl? Well, I do have 1 peak left. The carbonyl wouldn't show a peak because there's no hydrogen associated with it. But the last peak would be a CH3, and this integrates to 3. So this is starting to make sense here. Now the last question would be, if I have this C double bond O, where would I put it, and would it make sense to make the CH3 a singlet? So I wouldn't put the CH3 here, right? Because by putting it there, that makes it terminal. That would make an ether, and there would be no room for the last carbon and oxygen. So I would not go about putting the methyl there. It would make more sense for me to put the carbonyl because the carbonyl is not terminal. It can hold something else on the other side. And on the other side, if I put a CH3, would that make sense? Well, a methyl group next to a resonance stabilized group like a carbonyl is going to be around a 2 to a 3. So yes, that makes sense. Okay. And I come back down here. All of this should become a singlet because the carbonyl has no neighboring protons. So this would be the spec for ethyl acetate. And that is exactly what we have here. So notice, and you could have solved the degrees of unsaturation for this. It might have helped you. But when you look at this, for simplistic molecules, you tend to be able to solve the structure simply through the proton NMR alone. And that's why I have stressed throughout this, the proton NMR is the most useful of the specs. Now, that's just my opinion. There's no given fact about that. However, because of the splitting patterns and the integrations that you can pick up on, it's going to give you the ability to go through and deduce until you get to the most plausible structure. And you could even get a little more advanced than this and probably still get away with it. When you get into more complicated molecules, you want your mass spec and your IR. All right, so let's take a look at one more before we wrap up here. So here we have C8H8 and an oxygen. And again, I'll tell you the numbers. So don't worry about this peak here. That's your TMS in this case, the internal standard. All right, so the first one that we have is going to be about a 3.7. All right, and that 3.7 is associated with this singlet that we find right here. Then we have one, I'm actually going to write it up here so you can see it a little bit better. We have one around 7, it's just shy of 7, maybe like 6.95 ppm, and another one here at about 7.8 ppm. And then here we have one that is around 9.9 ppm. All right, so just from a glance, you should be able to gather a couple of things here. So first of all, the lowest ppm is 3.7, so we're dealing with all electronegative type of stuff here. We don't have any hydrocarbon sp3 hybridized that are going to be far away from electron withdrawing groups, because we would find those somewhere between probably 0.5 and 2. Now, what other information can I gather here? Well, between 7 and 8 is going to be where I would find aromatics. So I will propose that I have a benzene ring. Okay. And when I take a look at this, I've got an integration of 2 and 2 on these peaks here. So that means that I would have a di-substituted ring, and this is a little difficult to see in the resolution here, but this is a doublet, and this is also a doublet. So in terms of the splitting pattern. And because of that, that tells me that I have some level of symmetry here, okay, which means I'm going to have a para di-substituted compound. Now, the two substitutions must be different, so it's going to be an X and a Y here. And that's because if they were both the same, so if it was an X and an X, like let's just say it was a hydroxyl group and another hydroxyl group, in that case, all 4 of these would show up as one signal. They'd be symmetrical to one another. However, I have a difference here, so I've got protons A, and then I have a proton set B right here. Okay, so this is along the lines of what I'm looking at. And this makes sense because it integrates to 4 total, one of the signals being A, the protons that are A, and the others are B. So I have to find out what X and Y are going to be. Well, we already know what one of them will be because anything that shows up between 9 and 10 should be an aldehyde group. So this is an aldehyde proton. Aldehydes are terminal, so therefore this must be attached to something, and that something would be the ring. So I know that one group that I have is going to be an aldehyde. So let's redraw this ring up here. I'm going to have an aldehyde, and then the question is, what's really left? Well, let's take a look at what we've used. We have used 5 hydrogens, 4 for the ring, and then 5 because of the aldehyde. So that leaves 3 hydrogens. How many carbons have we used? 6 for the ring, 7 for the carbonyl, and then the oxygen was used for the aldehyde. So what does that leave? A CH3. So all that I have is a singlet that integrates to 3. That would make this a toluene type of structure. So you're going to have a methyl group on that benzaldehyde there. And that is how we would solve for that one. So hopefully everybody has got a grasp on this, and I wanted to go through and show you and prove to you you can do this type of problem solving simply through using your Proton NMR. That's how important Proton NMRs are. Now, it is obviously better the more information you have, so you want to try to couple them with carbon 13s and IRs and mass spec. So up next, we will take a look at that practice session that's going to tie everything together. Please remember to go over and visit the website at chemcomplete.com and give us a little engagement on the video. Leave a comment. We always try to respond back. And if you hit subscribe and the little bell, you will get notifications every time we're updating. We've got a new course coming out in August, and we're wrapping up here in July. So I hope to see everybody for the next lecture, and thank you as always for learning with us.